Billions of years ago, an ocean covering roughly a third of the surface of Mars may have quietly dried up and vanished, leaving almost nothing visible behind, except one specific, hard-to-spot piece of terrain, a flat band of land wrapping around an entire hemisphere of the planet, exactly where a coastline used to sit. Scientists just found it, and they're calling it a bathtub ring. Let's start with the honest framing right up front, because the actual story here is more interesting than a simple headline can capture. This specific discovery didn't come from a rover driving across the Martian surface. It came from scientists at Caltech carefully analyzing decades-old laser altimeter data collected from orbit and finding a pattern nobody had specifically searched for before. NASA's rovers, particularly Perseverance, have contributed real, separate evidence supporting the broader idea that Mars once had abundant water. But this specific bathtub ring finding is an orbital data discovery, published in the journal Nature on April 15, 2026, led by planetary geologist Abdallah Zaki alongside Caltech professor Michael Lamb. Here's the number that makes this genuinely significant. If this feature really does mark an ancient coastline, the ocean it once bordered would have covered approximately 1/3 of the entire surface of Mars, sitting somewhere between 1,800 and 3,800 meters below the Martian reference elevation, roughly 5,900 to 2,500 feet down, and the shelf itself stretches across about 7% of the planet's total surface area, forming a continuous band along the boundary between the southern highlands and the northern lowlands. I'm the host here at Today's Latest Analysis, and every claim in this video is pulled directly from the actual published research, not exaggerated for a headline. Subscribe now, because we cover real space science exactly like this, the moment new research drops. Let's start from the beginning, because to understand why scientists went looking for a bathtub ring on Mars in the first place, you need to understand a debate that's been running in planetary science for decades. This debate isn't new. The idea that Mars once held a northern ocean has actually been circulating in planetary science since the early 1990s, when researchers studying images from NASA's Viking orbiters first proposed that certain features in the northern lowlands looked like ancient shorelines. That original hypothesis sparked decades of back and forth in the scientific community. Some researchers pointed to apparent shoreline terraces as compelling evidence. Others argued those same features could just as easily be explained by volcanic flows, glacial activity, or simple erosion patterns that happened to resemble a coastline by coincidence. Without a stronger, more durable piece of evidence to settle the argument, the Mars ocean hypothesis spent more than 30 years sitting in scientific limbo. Plausible, genuinely interesting, but never quite proven or disproven. That's the exact stalemate Zaki and Lamb set out to break by looking for something more permanent than a shoreline in the first place. For years, researchers have debated whether ancient Mars had enough liquid water to form a genuine, long-lasting ocean, or whether its water was limited to smaller lakes, streams, and short-lived floods. It's widely accepted that Mars had liquid water on its surface at some point in its history. Orbital images clearly show what look like dried river channels and delta formations. But an ocean is a very different claim than a lake or a stream. Confirming an ocean requires evidence of a large, long-lived body of water, one that persisted stably for a significant stretch of time. Not just a temporary flood that came and went. Previous attempts to confirm a Martian ocean focused mainly on looking for ancient shorelines, the specific line where standing water would have met the land. The problem is that shorelines are extremely thin features, and on a planet that's experienced billions of years of volcanic activity and wind erosion, a feature that thin is exactly the kind of thing that gets worn away, buried, or deformed almost beyond recognition. That's exactly the problem Zaki and Lamb set out to solve. As Zaki put it directly, the team wanted to find a better topographic feature than shorelines that could serve as real evidence for an ocean. Here's the clever part of their approach. Instead of starting on Mars, they started right here on Earth, a planet where we already know oceans exist and can study exactly what geological features they leave behind. Using computer simulations, the team essentially drained Earth's own oceans virtually, watching to see which topographic features remained most clearly visible once the water was gone. The most distinct, most durable feature that survived that virtual draining wasn't the shoreline itself. IT was a much broader, flatter band of terrain, stretching up to several hundred kilometers wide, wrapping around the contours of where land meets ocean like a ring left behind around a drained bathtub. Geologists have a specific name for this feature here on Earth. It's called the continental shelf, and unlike a shoreline, which shifts constantly as sea levels rise and fall over time, a continental shelf is a large, relatively stable landform that persists largely unchanged over extremely long stretches of geological time. Once the team confirmed that a continental shelf was the more reliable signature to search for, they turned their attention to Mars, using topographic data collected by NASA's Mars Orbiter Laser Altimeter, known as MOLA, an instrument that mapped the surface of Mars from orbit using laser measurements, to build an extremely detailed elevation model of the entire planet. Analyzing that global elevation data, the team searched specifically for broad, flat, low-slope regions, exactly the kind of terrain a continental shelf should leave behind, and they found one. A wide band of terrain sitting between roughly 0.800 and 3,800 meters below the Martian datum, showing unusually low slope and curvature compared to the surrounding landscape, forming a continuous ring along the boundary separating Mars's southern highlands from its northern lowlands, precisely the region long suspected of once holding a northern ocean. It's worth understanding a little about the instrument that made this entire analysis possible in the first place. The Mars Orbiter Laser Altimeter flew aboard NASA's Mars Global Surveyor spacecraft, which operated in orbit around Mars for nearly a decade, beginning in the late 1990s. MOLA worked by firing a laser pulse down toward the Martian surface and precisely timing how long it took that pulse to bounce back, allowing scientists to calculate the exact elevation of the ground beneath the spacecraft's orbit with remarkable accuracy. Over thousands of orbits, that instrument built up a global elevation map of the entire planet, data so detailed and so enduring that researchers are still mining it for new discoveries decades after the mission itself ended. That's exactly the dataset Zaki and Lamb returned to, searching through terrain elevation patterns collected years before either of them started this specific project, for a signature nobody had specifically thought to look for before. The research itself was supported by Caltech, a Swiss National Science Foundation postdoc mobility fellowship, and the Jackson School of Geosciences Distinguished Postdoctoral Fellowship at the University of Texas at Austin, reflecting the kind of multi-institution collaboration that's become increasingly common in modern planetary science. Now, here's the second layer of this story, the part that shows genuinely careful, honest science rather than a team rushing to declare victory. The Martian shelf doesn't look exactly like Earth's continental shelves. There's an unexplained elevation change across parts of it that doesn't perfectly match what a simple, undisturbed coastal shelf should look like. Lamb himself was direct about this uncertainty, explaining that while the study shows some genuine telltale signs of a coastal shelf, it doesn't look identical to what we see on Earth. Meaning there's real evidence supporting the interpretation, but not evidence so complete that it settles the question outright. One possible explanation for that irregular elevation is billions of years of volcanic activity gradually shifting and deforming Mars's crust, warping the ancient shoreline out of its original, cleaner shape over time. But, as Lamb acknowledged plainly, that explanation is difficult to prove conclusively, which is exactly why whether this feature is truly an ancient shoreline signature remains a genuinely debated question within the research community, not a settled fact. What makes the case stronger, even with that uncertainty, is that this newly identified shelf doesn't exist in isolation. It sits in the same general zone where scientists have previously mapped deformed shoreline candidates, ancient river deltas, and other landforms and sediment deposits that are characteristic of a land-to-ocean transition on Earth. Multiple separate lines of evidence, collected using different methods over different years, are converging on roughly the same region of Mars, which is precisely the kind of pattern that makes planetary scientists take a hypothesis seriously, rather than dismiss it as a coincidence. This connects to a separate but related piece of evidence that's been generating its own excitement, and it's worth being clear about how it fits in, since it comes from an actual rover rather than orbital data. Back in July 2024, NASA's Perseverance rover, exploring Mars's Jezero crater, discovered unusual reddish rock formations, nicknamed leopard spots, on a target called Chayava Falls. Features that on Earth are sometimes associated with chemical reactions involving organic material and microbial activity, though scientists have been careful to describe them as a potential biosignature requiring much more analysis, not confirmed evidence of ancient life. The finding doesn't directly prove the ocean hypothesis. Jezero crater itself is understood to have hosted an ancient lake rather than sitting directly on the proposed coastal shelf, but it adds to a broader cumulative picture building across multiple missions and multiple types of evidence, all pointing in the same general direction, that ancient Mars held onto significant amounts of liquid water for far longer and in far greater quantities than the cold, dry, dust-covered planet we see today would ever suggest. Separately, other recent Mars research has continued adding supporting context to this same broader picture. Scientists studying ancient sand dunes in Gale Crater found evidence that groundwater likely soaked the region long after surface water had already begun disappearing, suggesting Mars may have remained at least partially habitable for a longer stretch of its history than previously assumed. Other researchers have identified large valley systems, including one stretching roughly 1,300 kilometers near Mars' equator, that show signs consistent with ancient water carving through the landscape alongside volcanic activity. None of these individually proves the existence of a full ocean, but together they paint a picture of a planet that once cycled water through rivers, lakes, underground reservoirs, and possibly a genuine ocean in ways that look far more familiar and far more Earth-like than the Mars we send rovers to explore today. So here's why this specific discovery matters so much for the broader search for life beyond Earth. If Mars really did host a long-lived ocean, stable enough to carve out a genuine continental shelf over what would have needed to be millions of years, that represents an extended window of time in which liquid water, widely considered one of the essential ingredients for life as we understand it, existed in large, stable quantities on another planet's surface. Coastal environments on Earth are particularly rich zones for biological activity and fossil preservation. River sediment mixing with ocean water, nutrients concentrating along the shoreline, environments that are unusually good at both supporting early life and preserving evidence of it long after the water itself disappears. If ancient Mars had a genuine coastal zone in the same location this new shelf occupies, sedimentary deposits along that ancient coastline could theoretically have preserved signs of past biological activity. The same way coastal sediments here on Earth continue to preserve fossil records from our own planet's history. That's precisely why this discovery is already shaping the target list for future Mars missions. The European Space Agency's Rosalind Franklin rover, specifically designed to search for signs of ancient biological activity by drilling deeper beneath the Martian surface than any previous mission saw, is expected to study regions connected to this ancient water history once it begins operating on the surface. As Zaki noted, this shelf discovery is a strong additional piece of evidence supporting the case for a northern ocean on Mars, but there's still plenty of follow-up work required, including having rovers directly examine sediment deposits in the region and further analysis of the satellite data that first revealed the pattern. It's worth being direct about where the science genuinely stands right now, because that honesty is exactly what separates real research from an exaggerated headline. This discovery does not confirm that Mars definitely had an ocean, and it certainly doesn't confirm that life ever existed there. What it does provide is a second, independent, physically grounded line of evidence built from an entirely different analytical approach than previous shoreline studies that converges on the same region and the same general conclusion that earlier, separate evidence had already pointed toward. In science, that kind of convergence, multiple different methods independently arriving at a similar answer, is usually how confidence in a genuinely difficult hypothesis is built over time, one careful, honestly caveated study at a time, rather than through a single dramatic announcement that claims to have solved the question outright. Mars today is a cold, thin-aired, dust-covered world, a planet that looks nothing like the blue, ocean-covered Earth we're used to. But if this shelf really does mark where an ancient coastline once sat, it means that billions of years ago, for a genuinely long stretch of time, Mars looked far more like our own planet than most people ever imagine when they picture the red planet, a world with rivers feeding into a real ocean, waves shaping a real coastline, and sediment quietly building the same kind of geological feature that still rings every continent here on Earth today. I'll bring you the next update the moment any rover mission begins, directly sampling this proposed coastal shelf region, or if new satellite analysis adds further support to, or challenges, this specific interpretation. If you want real Mars, science explained clearly, separating what's actually confirmed from what's still genuinely being debated, that's exactly what we do here every time research like this gets published. Drop a comment and let me know what surprised you most about this discovery, the sheer scale of a third of the entire planet once being covered by ocean water, or the fact that scientists found this evidence by first testing their method against Earth's own oceans before ever pointing it at Mars. Subscribe so you don't miss the next update. Share this with anyone who'd find real planetary science genuinely fascinating, and I'll see you in the next one.